The universe is a cathedral of silence, a darkness so vast, so unbroken, that even the brightest stars are nothing more than fragile embers adrift in an eternal sea. Across this abyss, light is the only messenger, its beams stretching outward, with patient slowness, taking millions, even billions, of years to reach a waiting eye. To see the heavens is to gaze into memory, to witness a past already vanished. Every glimmer in the sky is a ghost. Every galaxy a fossilized flame dot here. Distance is destiny. Time and light are inseparable rulers. Nothing outruns them. Nothing dares disobey causality, and yet something does. A signal, faint but undeniable, arrives not when it should, but before. Too early, impossibly early. A ripple through space-time, a whisper of particles, a murmur from the stars out of sequence. With the cosmic clock, it is like hearing an echo before the sound, like glimpsing a shadow before the object itself. Subtle, almost imperceptible, yet devastating in meaning. For if a signal can outrun its cause, then the arrow of time bends. Cause and effect lose their order. The fabric of reality, phrase, is it a mistake of our instruments, a trick of interpretation? Or is it something deeper, that the universe itself is not whole, but porous, a manuscript read out of order, its pages shuffled by unseen hands? This is the story of that signal, of neutrinos that arrive before the light of dying stars, of quantum particles that defy distance, of gravitational waves that sometimes whisper before the storm. It is the story of physics under siege, and it begins with a question that feels less like science and more like prophecy. What happens when a signal outruns time itself? The early 20th century reshaped everything humanity thought it knew about space, time, and motion. In 1905, Albert Einstein unveiled his special theory of relativity. It carried with it an unyielding decree: nothing could travel faster than light in a vacuum. Light was not just swift, it was the universe's law. Its speed, 299,792 kilometers per second, became the upper bound of existence. No signal, no particle, no form of energy could ever outpace it. To do so would be to tear causality itself apart. 10 years later, with his general theory of relativity, Einstein did more than set a limit. He wove a new vision of reality. Space-time was not a passive stage, but an active fabric. Gravity was not a force, but a bending of geometry itself. And within this geometry, cause and effect were sacred. Events flowed in one direction, guarded by the speed of light. The cosmos was a book written in order. Each page turned only after the one before. Einstein's colleague, Hermann Minkowski, was among the first to see the radical implication. Space and time were not separate. They were one fabric, inseparably interwoven, a four-dimensional continuum. Within this fabric, the speed of light did more than define a limit, it preserved the order of reality itself. But almost as soon as the ink dried on relativity's equations, cracks began to appear. Small ones at first, subtle and puzzling. Cracks that hinted that the speed of light was not always the perfect guardian it seemed. The first hints came from the stars. In February of 1987, astronomers around the world turned their telescopes toward the southern skies. There, in the large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way, a massive star had reached the end of its life. It collapsed and detonated in a brilliant supernova, later named SN 1987A. For weeks, its light blazed across the heavens, a once-in-a-lifetime event for modern science. But before its visible light ever arrived, something stranger happened. Underground, in the vast caverns of Japan's Kamiokande 2 neutrino detector, a signal appeared. Small flashes of light inside enormous vats of pure water revealed the passage of elusive particles, neutrinos, tiny ghosts of matter that barely interact with the world at all. Just a handful of them arrived, but they told a story no one expected. They had reached Earth nearly 3 hours before the visible light of the explosion. How could that be? According to every model, neutrinos and photons should have left the collapsing star at nearly the same moment. Light might be slowed by the dense stellar debris, yes, but hours of difference. To some, it looked like neutrinos had outrun light itself. The anomaly echoed louder with time. Cosmic rays charged. Particles arriving from deep space were found to possess energies so extreme that by theory they should not have survived the journey. According to the Grisen's spin-Kuzmin limit, intergalactic space should strip these particles of energy long before they reached Earth. Yet detectors caught them, intact and defiant, as though they had traveled by routes unknown, perhaps faster than they should have been able. At the quantum scale, an even stranger defiance appeared. In the 1960s, physicist John Bell sharpened one of Einstein's lingering doubts about quantum theory. Einstein had derided entanglement pairs of particles linked across distance, says spooky action at a distance. He believed no real influence could leap across space faster than light. But Bell formulated a test, an inequality that could prove whether entangled particles truly behaved as quantum theory predicted. By the 1980s and 1990s, experiments confirmed it. Entangled particles influenced each other instantly, correlations appearing without regard for separation. One particle measured in Europe, the other in America, and their states aligned immediately. No signal traveled between them in any conventional sense, but the result mocked the very notion of distance. It was as if the universe itself refused to respect its own speed limit. Then came the most haunting messenger of all, space-time itself. In 2015, the twin detectors of LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded something extraordinary. Ripples in space-time gravitational waves washed across Earth, born from the collision of black holes a billion light-years away. It was the first time humanity had ever heard the universe tremble. But as the years unfolded, another puzzle arose. Sometimes gravitational waves arrive just before the visible flare of cosmic explosions. Gamma-ray bursts, supernova, merging neutron stars. The light came, yes, but a whisper of space-time had already reached us first. Was it merely the difference in how light escapes dense matter compared to gravity's immediate ripple? Or was it something deeper, a sign that not all cosmic messengers obeyed the same timing? Each anomaly, taken alone, might have been dismissed. Neutrinos slipping free earlier than photons. Cosmic rays surviving against the odds. Entanglement. Correlations mocking distance. Gravitational waves arriving before light. Each could be explained, adjusted, rationalized, but together they suggested a pattern. A quiet rhythm beneath the cosmos. A suggestion that sometimes signals do not wait their turn. Sometimes they arrive too soon. Behind every puzzle stood scientists straining to understand. In Japan, Masatoshi Koshiba, pioneer of neutrino astronomy, marveled at SN 1987 AS, early arrivals data that would win him a Nobel Prize. In Europe, physicists tested Bell's inequalities again and again, confirming the eerie reach of entanglement. In America, the LIGO collaboration stretched laser beams across kilometers, searching for tremors in space-time and finding them ahead of expectation. Each discovery added weight to the same suspicion. Relativity's speed limit was firm, yet reality sometimes seemed to bend around it. Albert Einstein had tried to safeguard causality with mathematics. John Bell had tried to break it open with thought experiments. Astronomers and physicists, buried in observatories or underground chambers, had tried to capture the faintest of signals, and what they saw was troubling. For the first time, humanity had reason to ask, is the universe telling its story in order? Or are we seeing shadows before objects, echoes before voices, effects before causes? The discovery phase of this mystery was not a single moment, but a rising chorus. A chorus that began with relativity's proclamation that nothing outruns light. A chorus that deepened with neutrinos arriving early, cosmic rays breaking limits, particles defying distance, and space-time itself whispering before stars. Each signal was like a word out of place in a sacred text, small enough to doubt, yet loud enough to change meaning. Together, they asked the question that science could not easily silence. What happens when a signal arrives too soon? For centuries, light had been considered the ultimate courier of truth. From Galileo's lantern experiments to Maxwell's elegant equations, light was seen as the boundary between what could be known and what could never be reached. When Einstein crowned it with the throne of cosmic law declaring, its speed, the ceiling of causality science, exhaled with certainty. The cosmos had boundaries, yes, but they were clear, logical, and absolute. But then came the signals, early neutrinos, cosmic rays, entanglement, correlations, gravitational ripples whispering ahead of light. Each arrival, slightly premature, carried with it a subversive undertone. They did not merely confuse measurement. They threatened the very scaffolding upon which reality stood. The shock was not that an anomaly appeared. Science thrives on anomalies. The shock was that the anomalies touched the untouchable. The speed of light, causality, the arrow of time. Einstein's theory of relativity is built upon a cornerstone. Nothing can outrun light in a vacuum. If something were to surpass it, equations collapse into paradox. Cause and effect lose their order. An event in one frame of reference might appear reversed in another. A signal traveling faster than light could, under relativity's rules, arrive before it was ever sent. The messenger would precede the message. Such a reality would unravel the universe as a coherent story. Futures could bleed into presents. Effects could create their causes. Time itself would cease to be an arrow and become a loop of contradictions. This was not abstract philosophy. It was a hard limit, written into the geometry of space-time. The constancy of light speed was not a preference of physics, it was its spine. Without it, relativity, causality, and determinism fractured. So when particles seemed to arrive too soon, the suggestion was devastating. In 2011, the world of physics quivered. The opera experiment in Italy announced results that stunned even the most cautious. Neutrinos fired from CERN near Geneva to the Gran Sasso laboratory appeared to have traveled faster than light itself, by a margin infinitesimally small, but catastrophically important. The ghostly particles had outrun the cosmos' most sacred law. For weeks, headlines proclaimed a revolution. Had the ultimate limit been shattered? Was Einstein wrong? Was the universe more porous than believed? The physics community shuddered with both excitement and dread. If true, the implications were seismic. Tachyons, long dismissed, hypothetical. faster than light particles, would suddenly seem plausible. The door to time travel long locked would creak open, but the celebration was short-lived. A loose fiber-optic cable was eventually blamed for the anomaly. The neutrinos had not broken light's barrier. The instruments had erred. Relativity was safe, yet the episode left scars. For a brief window, humanity had glimpsed what it would mean if a signal truly outran causality. And even after the error was found, the question lingered. What if one day the anomaly could not be explained away? Even without opera, entanglement continued to haunt the physics community. Quantum experiments confirmed correlations between particles separated by kilometers, even hundreds of kilometers. The instant nature of their alignment did not technically allow information to travel faster than light. No usable message could be sent this way. But the effect still mocked the idea of locality. Einstein himself despised the notion, labeling it spooky action at a distance. For him, it was an affront to common sense and to relativity alike. Yet experiment after experiment upheld it. By the 21st century, entanglement was not only verified, was being harnessed for quantum communication. The philosophical unease remained. If the universe allowed correlations that seemed instantaneous, was relativity truly inviolable, or only mostly so? The signal arriving too soon was no longer just a possibility. It was a shadow lurking at the edge of every quantum lab. The neutrino arrival from SN 1987A still hung like a riddle over astrophysics. Hours before visible light, a handful of neutrinos had struck detectors deep underground. Conventional explanations were offered. Perhaps photons were delayed by the dense stellar material while neutrinos slipped through. Perhaps the star's collapse released neutrinos slightly earlier than light. But none of these erased the unease, because even a few hours of discrepancy raised a forbidden thought. What if space-time itself allowed multiple clocks, slightly misaligned, slightly fractured? What if signals could take shortcuts through geometry that light could not? The shock was not in the hours gained. It was in what those hours implied, the potential bending of causality itself. Then came the era of gravitational astronomy. LIGO's first detection of rippling space-time in 2015 inaugurated a new era. Humanity could listen to the tremors of the universe as never before, but with listening came dissonance. On several occasions, gravitational waves seemed to be recorded just before the bursts of light or gamma rays that accompanied them. Physics had answers, yes. Gravitational waves escape immediately from cataclysmic mergers, while light may be delayed by surrounding debris. Still, too many, the eerie effect remained. The whisper of space-time arriving before the scream of matter. It was a subtle but haunting inversion, an echo before the sound. The scientific shock was not simply that anomalies existed, it was that they gnawed at the threads holding reality together. If neutrinos truly outran light, if entanglement truly mocked distance, if gravitational waves truly arrived before light, it meant space-time might not be as coherent as Einstein envisioned. It meant the narrative of the universe was not necessarily sequential, but perhaps fractured, shuffled, rewritten. The fear was not only scientific, but existential. A universe where signals could arrive too soon was a universe where time itself could no longer be trusted. The comforting order of cause and effect would dissolve. The laws that bound galaxies, stars, and atoms might be fragile illusions. Humanity's understanding of reality would be revealed as provisional, not eternal. Einstein had always resisted such ruptures. He could not accept that nature would permit causality to fail. His debates with Niels Bohr and others were filled with this resistance. His insistence that the universe must be rational, consistent. Decades later, Stephen Hawking offered a caution. Perhaps there exists a chronology, protection, conjecture, a law of nature that prevents time, paradoxes, safeguarding causality even when theory tempts it, yet the anomalies linger. If such a law exists, it is hidden, subtle, and unproven. The possibility remains that one day a signal will arrive too soon in a way no loophole can explain away. The scientific shock is not only about physics, it is about meaning. A signal that outruns light is not merely fast, it is sacrilegious. It questions the very sequence of reality. It invites paradoxes where an effect might precede its cause, where the future might influence the present. Such a cosmos is not only strange, it is terrifying. For if reality does not unfold in order, then the human sense of past, present, and future is a fragile illusion. Our memories, our decisions, even our very sense of existence could be revealed as echoes in a universe where time does not flow, but folds. That is why the anomalies shake science so profoundly, not because they break instruments, but because they threaten to break the story of reality itself. And so the question persists, haunting every lab, every observatory, every calculation at the edge of physics. What happens when a signal arrives before its cause? The anomalies were unsettling, yet science does not rest upon unease. It sharpens it into questions, builds instruments, and tests. When signals seemed to arrive too soon, physicists did not retreat. They dug deeper into the bedrock of reality, with tools of greater precision than ever before. The 20th century had given birth to relativity and quantum mechanics, two pillars that refused to merge. The 21st century gave rise to a generation of machines and collaborations designed to interrogate those cracks, to ask if signals out of sequence were mistakes of perception or whispers of new physics. Beneath mountains, under kilometers of rock, and even encased in the silent ice of Antarctica, detectors were built to hunt the faintest messengers, the neutrinos. Super Kamiokande in Japan, a cathedral of pure water, watched for the faintest flashes as neutrinos collided with atoms. Ice cube, buried in the Antarctic ice sheet, transformed a cubic kilometer of frozen water into a telescope that looked inward, not outward. These machines were not designed to catch light, but its elusive rivals ghost particles that rarely interact, yet reveal truths photons cannot. When neutrinos from supernova arrived before light, physicists asked, was this an artifact of astrophysics or a fracture in spacetime's order? To answer, detectors timed arrivals to the millisecond, tracing correlations between bursts and flashes, comparing across continents. The data suggested a partial explanation. Photons could be delayed as they escaped stellar debris, while neutrinos, nearly massless, slipped through unimpeded. Yet the timing discrepancies were not always so easily reconciled. A hint remained an open door that some dared not close. At CERN and Fermilab accelerators hurled neutrinos across hundreds of kilometers, testing whether they honored light supremacy. The opera controversy had left scars, but also inspiration. Better synchronization, tighter calibrations, atomic clocks more precise than ever were brought to bear. Run after run, neutrinos were measured against the cosmic limit. The results were clear. They traveled close to light speed, unimaginably close, but not beyond. Relativity held. Yet the investigations refined human tools, squeezing error margins smaller. preparing for the day when a true anomaly might appear. Again and still, cosmic neutrinos, those born in stellar collapse or active galactic nuclei, remained less predictable. Their journey was long, their origins complex. Any signal out of place carried both the burden of astrophysical mystery and the allure of fundamental discovery. If neutrinos flirted with light's boundaries, entanglement defied boundaries altogether. In labs across the world, particles were paired, separated, and tested. One spun clockwise, the other counterclockwise. One polarized vertically, the other horizontally. Their fates were locked in harmony, even when distance separated them by kilometers. Physicists closed loophole after loophole, proving the correlations were real, immediate, undeniable. No signal faster than light could be sent through entanglement, carried no usable information, yet the effect remained. It was as though the universe itself kept two particles in a single state. Across vast divides, ignoring distance and time alike, John Bell's inequalities, once a mathematical exercise, became a touchstone. Their violation by experiment after experiment confirmed the non-local character of quantum reality. If signals seemed to arrive too soon, entanglement was the most haunting echo, proof that reality was stitched by threads invisible to relativities. Geometry, gravitational waves added a new voice to the investigation. LIGO, Virgo, and later Cagra tuned their arms to space-time itself, listening for ripples born in collisions of black holes and neutron stars. When a merger was detected, telescopes on Earth and in orbit swiveled to catch its light. Timing was everything. In some cases, light followed within seconds. In others, hours passed. The gravitational wave was always first. The explanation seemed simple. Space-time's ripples escape instantly, while photons must fight through debris. Yet the effect unsettled, because to human eyes, it appeared as though the signal of gravity had outrun the signal of light, and deeper questions emerged. Could there be cases where gravitational waves themselves might arrive too soon, not by seconds, but by breaking the very rule of causality? The search was on, each detection scrutinized for discrepancies, each timing analyzed to the millisecond. Beyond the laboratories and detectors lay the oldest signal of all, the cosmic microwave background. This faint afterglow relic of the Big Bang carried secrets about the universe's infancy. Its smoothness across the sky posed a paradox. Light had not had time to cross the universe's expanse, yet the background appeared uniform. Something had synchronized distant regions before light could possibly connect them. The inflationary model was born a theory that space-time itself expanded faster than light in the earliest instant, stretching causality beyond recognition. If true, the universe had already demonstrated that signals could outrun light not as particles, but as the expansion of space itself. The early signal had been written into the fabric of the cosmos. In 2014, sensors recorded a meteor blazing into Earth's atmosphere. Its velocity seemed anomalous, too fast to belong to the solar system, perhaps interstellar in origin. Years later, analysis suggested something stranger. Its composition and speed hinted at a possibility beyond interstellar. Some speculated it might even have originated before our universe's expansion slowed. A messenger from epochs where signals obeyed different rules. Expeditions to recover fragments from the ocean floor began. Each shard could hold isotopic fingerprints, telling whether it obeyed our cosmic laws or carried whispers of another. If confirmed, it would be a signal, not of light or neutrinos, but of matter itself, arriving too soon from beyond the expected boundaries. As the evidence mounted, patterns emerged. Some cases could be explained. Neutrinos arriving before photons were natural in stellar collapse. Gravitational waves preceding light were expected in mergers cloaked in debris, but not all. Some anomalies defied easy resolution. Some data hinted at deeper irregularities, beyond error bars and astrophysical clutter. Physicists began to ask if the anomalies shared a root cause. Was space-time itself elastic, bending in ways relativity only approximated? Was the vacuum unstable, its quantum fields trembling with leaks that let signals slip ahead? The investigations deepened into speculation, yet the data forced the question: were these anomalies accidents, or were they signs of fractures in the fabric of reality? After decades of study, the haunting realization emerged: sometimes the universe does not play by its own rules, at least not by the rules as humanity understands them. Neutrinos, entangled states, gravitational whispers, cosmic uniformity each hinted that the universe may allow messages to travel out of sequence, arriving not late, but early. Perhaps time itself is elastic. Perhaps causality is not absolute, but contextual. Perhaps the signal that arrives too soon is not an error, but a truth we cannot yet frame. Science had not solved the mystery, but it had sharpened it, refined it, prepared humanity for the next escalation. For if signals could arrive too soon, then perhaps reality itself was unstable. Perhaps the laws we cling to are provisional, fragile, subject to collapse. The investigation had reached its limit. Beyond lay the deepening terror, the recognition that the mystery was not shrinking, but growing. The story might have ended with resolution. The anomalies could have been chalked up to debris, astrophysical quirks, or instrumental error. But the universe rarely closes its books so easily. The deeper scientists looked, the stranger the signals became. Instead of fading, the mystery intensified. Instead of retreating, it escalated. When signals arrive too soon, they violate the most sacred principle of physics, causality. The order of events, the structure of time itself, depends on signals obeying limits. Cause must precede effect. The sun must shine before its light touches. Earth, a supernova, must collapse before neutrinos or photons can escape. But anomalies suggested otherwise. A neutrino burst detected before the stellar explosion became visible. Gravitational waves echoing seconds before the electromagnetic blaze. Quantum entanglement correlations manifesting instantaneously, as if time and distance were irrelevant. Each case was a small fracture, but together they pointed toward something profound. The universe may not be bound to a single timeline, a single order. Perhaps it could whisper ahead of itself, leaking hints of the future into the present. Entanglement became the most extreme example. Particles separated by kilometers, or even hundreds of kilometers, responded instantly to one another. No signal passed between them, at least not in any way science could measure. Yet their states were synchronized. Einstein had derided it as spooky action at a distance. But modern experiments, closing loophole after loophole, left little room for denial. Entanglement correlations were real. They were instantaneous. And if they could not be explained by signals traveling through space-time, then perhaps they existed outside of space-time altogether. This was the escalation. What if some signals are not signals at all, but manifestations of a deeper order, one that transcends the geometry of relativity? Cosmology presented another fracture. The cosmic microwave background, mapped in exquisite detail, was astonishingly smooth. Regions of sky separated by billions of light-years shared nearly identical temperatures, even though light had not had enough time since the Big Bang to cross. Between them, this was the horizon problem, distant parts of the universe behaving as though they had communicated, even though, by all laws of relativity, they could not have. Inflation theory was proposed as a solution a moment in the earliest fractions of a second when space itself expanded faster than light, carrying information across vast distances. If true, then the universe itself had once allowed faster-than-light connections. Not particles, not waves, but space-time itself outrunning causality. Here the escalation deepened again. If space-time could exceed its own limit in the past, could it do so again? Could signals outrun time because the very structure of the cosmos permits it under hidden conditions? Speculation grew bolder. Wormholes' solutions of Einstein's equations were resurrected as possible culprits. These hypothetical tunnels connected distant points in space-time, folding the fabric like paper so that two faraway places became adjacent. If such a wormhole existed, a signal could vanish in one region and appear instantly in another, arriving impossibly early. The problem was stability. Wormholes, if they exist, are unstable, collapsing faster than light itself can traverse them. Exotic matter with negative energy would be required to keep them open, a material not yet found. Still, their mathematics haunted cosmology, for if wormholes were real, then a signal that arrived too soon might be evidence not of broken causality, but of hidden pathways through the geometry of reality. Another threat came not from hidden tunnels, but from the cosmos itself. Observations showed that expansion was accelerating, driven by dark energy. If that acceleration continued unchecked, it could lead to the Big Ripper future where galaxies, stars, and eventually atoms themselves would be torn apart as space-time stretched infinitely. In that scenario, signals would precede their causes because the fabric connecting events would shred. Communication itself would unravel. A flash from a star might arrive before the star itself collapsed, not because the signal traveled faster than light, but because the background against which it moved was dissolving. This was more than speculation. It was a reminder that cosmic acceleration was not fully understood. And if the laws governing expansion could bend so far, perhaps signals out of order were only a foretaste of deeper ruptures to come. In the cosmic microwave background, some physicists claimed to see faint anomalous patterns, circular scars, or bruises on the sky. These, they argued, might be evidence of collisions between our universe and others, bubble universes bumping against one another in the sea of the multiverse. If such collisions occurred, signals from beyond could bleed into our cosmos, appearing before their sources could be reconciled. A signal arriving too soon might not be from our universe at all, but from another reality pressing against our own. The evidence remained controversial, disputed, perhaps illusory, yet the possibility lingered. The signal that arrived too soon might be the whisper of another cosmos. Each of these escalations led to the same dreadful possibility. The universe itself may not be coherent. If signals can arrive before their causes, then reality's narrative collapses. The past, present, and future lose their order. For physicists, this was more terrifying than destruction. The universe ending in fire or ice was one thing. The universe ceasing to make sense was another. If time's arrow bent, if causality cracked, then no law, no prediction, no measurement could be trusted. Reality itself would unravel not as a physical event, but as a logical catastrophe. The anomalies could no longer be dismissed as isolated. Neutrinos arriving first, gravitational waves whispering before light, entanglement correlations appearing outside of time. The cosmic microwave background smooth beyond reason. Each was a piece of a pattern. The cosmos was not a perfect machine ticking forward in neat order. It was messy, elastic, unstable. The signal that arrives too soon was not a single event, but a symptom of something deeper. Space-time may not be absolute. Instead, reality might be layered, provisional, fragile. And when those layers shift, signals slip free, arriving ahead of schedule, like cracks appearing before a collapse. And then came the ultimate escalation. Perhaps signals arriving too soon are warnings. If the universe allows causality to bend even slightly, then its stability may be in doubt. A single fracture could spread. A tear in space-time could cascade, rewriting physics at the speed of light, annihilating all structures of matter and law. That this is false vacuum decay, the idea that our universe resides in a metastable state, a false equilibrium. If disturbed, it could collapse into a lower energy state, altering every constant of nature. Such an event would expand at the speed of light. To those awaiting it, it would appear as the ultimate signal arriving too soon, the end of physics, the rewriting of existence, the annihilation of causality. No warning would precede it. No survival would follow. The escalation reached its peak. With a haunting suspicion, perhaps signals arrive too soon because our understanding of time is incomplete. Perhaps past and future are illusions, the product of limited perception. Perhaps the universe is not a sequence, but a whole. And signals are not traveling forward or backward. They are simply revealing different slices of the same eternal fabric. In this view, the anomaly is not a violation, but a glimpse, the future, pressing against the present, the cosmos whispering its secrets out of turn. When anomalies refuse to vanish, science turns to its most dangerous tool, imagination. The signal that arrives too soon could be an error, a coincidence, a misunderstanding. Yet, if it is real, if it persists across instruments and domains, then it demands theories. It demands that physics itself stretch to explain the impossible. What follows is not certainty, but speculation, visions of what reality might be if causality can bend. The most cautious explanations are also the most comforting. Perhaps photons from supernova are delayed by dense stellar debris, while neutrinos slip out first. In this view, the early arrival is not impossible, only a natural ordering of physics. Similarly, cosmic rays with impossible energies might have been accelerated by unknown astrophysical engines, not by violations of relativity. Gravitational waves might ripple through space-time earlier than photons because light is trapped or scattered, while space-time itself passes freely. These anchors preserve Einstein's order, keeping light as the cosmic limit. They reassure physicists that anomalies can be absorbed into existing frameworks, but the cracks remain. And when cracks multiply, speculation expands. Entanglement remains the most unsettling case. Though no usable information is transmitted faster than light, the correlations defy locality. It is as though particles share a hidden script written outside of space-time. Some physicists argue that entanglement proves space-time is not fundamental. Instead, it may be emergent, arising from deeper connections of information. In that deeper substrate, Distance and time may not exist as we know them. Signals arrive too soon because, in that hidden realm, soon and late are meaningless. This theory does not merely explain anomalies, it rewrites the stage itself, suggesting that space-time is not the final reality but an approximation of something deeper. Long ago, equations hinted at hypothetical particles that always travel faster than light tachyons. They were dismissed as mathematical curiosities, unstable and unphysical. Yet they linger in the imagination. If tachyons exist, they would always outrun light, always arrive before expected. Their presence would fracture causality, allowing effects before causes, futures bleeding into presents. Though no tachyon has been detected, the concept haunts theories of fields and symmetry. If a signal truly outruns light, tachyons may be its messengers, the hidden wanderers of physics. General relativity allows solutions where space-time folds back upon itself, creating bridges between distant points, wormholes. If such structures exist, then a signal may vanish in one region and emerge instantly in another, appearing impossibly early. To observers, it would seem faster than light. In truth, it would have taken a shortcut through a higher geometry. The difficulty lies in stability. Wormholes require negative energy to remain open. Yet quantum theory does permit negative energy in fleeting amounts, the Casimir effect between plates, tiny gaps in the vacuum. If nature could amplify such effects, wormholes might exist. And if they do, the signal that arrives too soon might be the whisper of matter or energy sliding through cosmic tunnels. Cosmology offers another path. In the first instant of the universe, inflation theory proposes that space itself expanded faster than light. Galaxies were carried apart on a wave of expansion that exceeded the cosmic limit. In that epoch, signals could leap vast distances in no time. Information might have spread across the universe before light could catch up, explaining the horizon problem, the eerie smoothness of the cosmic microwave background. If inflation happened once, could it happen again? Could local patches of space-time inflate, allowing signals to outrun the rules? A burst of expansion, invisible but real, could deliver a signal ahead of schedule. Some theories expand the canvas beyond a single universe. Eternal inflation suggests that our cosmos is but one bubble among countless others, each with its own laws of physics. These bubbles may collide, imprinting scars, sending signals across boundaries. A signal that arrives too soon might not belong to our universe at all. It might be the echo of another cosmos pressing against ours, its physics bleeding into our detectors. In this view, the anomaly is not a violation but a message from elsewhere. From beyond, such collisions could explain faint anomalies in the cosmic microwave background, strange alignments, cold spots. If real, they would mean that the signal too soon is the first proof of the multiverse. Perhaps the most terrifying speculation is that of vacuum decay. According to some models, the Higgs field, the field that gives particles mass, may not be in a stable state. Instead, our universe may rest in a false vacuum, a temporary plateau of energy. If disturbed, it could collapse into a lower energy state. A bubble of new physics would expand at light speed, rewriting particles, forces, and laws. To observers, it would appear as the ultimate early signal, the end of everything, arriving with no warning, no cause. If the signal that arrives too soon is real, some physicists whisper it might be a foretaste of such instability, a cosmic hint that our universe is temporary, fragile, balanced on the edge of collapse. Another vision comes from the holographic principle, the idea that the universe is not three-dimensional, but a projection of information stored on a distant boundary. If reality is a hologram, then signals may appear early because causality is not anchored in space, but in information itself. In this view, the universe is a vast computation, and signals that arrive too soon are simply glitches in perspective, information flowing along the boundary rather than through the bulk. The early arrival is not faster than light, but outside of light. A reminder that space is illusion. Some speculations move beyond physics into realms of near myth. Signals too soon could be whispers of advanced civilizations manipulating space-time, folding distance, or creating artificial wormholes. They could be evidence that consciousness itself interacts with the quantum substrate, pulling correlations across time. Others suggest that reality itself is not singular, but layered like a palimpsest. In those layers, different versions of events coexist. A signal arrives too soon, not because it traveled faster, but because we glimpsed a neighboring layer, a parallel script of existence, though extreme. These visions remind us that anomalies press not only against equations, but against imagination. All these theories, conventional anchors, entanglement, tachyons, wormholes, inflation, multiverses, vacuum decay, holograms share one theme. They suggest that space-time is not absolute. It is not the final stage, but a provisional construction. If the signal that arrives too soon is real, then our universe is not a clockwork of rigid laws, but a fabric that can bend, tear, or reveal deeper layers. Causality, the most sacred law, may be a shadow of something larger. In that shadow lies both terror and wonder. Terror, because if causality fails, then reality itself can collapse into incoherence. Wonder, because if causality bends, then perhaps hidden truths can emerge, new dimensions, new universes, new orders of being. Theories and speculations do not solve the mystery, but they keep it alive. They remind humanity that science is not only about answers, but about questions, questions that stretch imagination to its edge, questions that transform anomalies into possibilities, and among them all, one question remains: is the signal that arrives too soon a mistake, or the first glimpse of a universe beyond time? The signal that arrives too soon cannot remain a ghost story. To test it, humanity builds machines as vast as cathedrals, instruments as delicate as whispers, eyes that stretch across the cosmos and ears that press against the silence of space-time. If anomalies threaten to undo physics, then science answers with observation. This is the age of tools machines, designed not merely to measure, but to ask reality whether it is consistent, whether time itself is as stable as we believe. In 2015, the Laser Interferometer Gravitational Wave Observatorial (IGO) detected the first trembling of space-time from colliding black holes. The signal arrived as a faint ripple, stretching and compressing arms 4 kilometers long by less than a proton's width. What astonished scientists was not only the detection, but the timing. Sometimes gravitational waves seem to reach Earth before light from the same cataclysm. Telescopes scramble to confirm, but light lags behind. Is it absorbed, delayed, or is space-time itself delivering its signals out of order? Virgo in Italy and Kagra in Japan extend this listening network. Together, they triangulate the sky, tracing ripples of space-time with precision. Each detection tests whether signals obey Einstein's speed limit or whisper of something faster. Deep beneath mountains and ice, neutrino observatories wait. Super Kamiokande in Japan, a tank of 50,000 tons of water, watches for blue flashes as ghostly particles strike. IceCube at the South Pole buries thousands of sensors into a cubic kilometer of ice, transforming Earth itself into a detector. When a star collapses, neutrinos escape first, racing outward before light can free itself. In 1987, they arrived hours early from supernova 1987A. Since then, detectors have sharpened their timing, prepared to catch the next stellar death if neutrinos once again arrive too soon. Earlier than models predict, it will force a reckoning. Are they slipping through shortcuts in space-time? Are they harbingers of physics beyond relativity? The James Webb Space Telescope does not listen for ripples or ghost particles. It gazes back to the dawn of time, capturing galaxies formed only a few 100 million years after the Big Bang. Already, Webb has revealed structures too large, too early, galaxies that should not yet exist. To some, this feels like another signal that arrived ahead of schedule universe, forming faster than theory permits. If light itself can betray chronology, if galaxies appear before physics allows, then perhaps time's arrow is not as rigid as believed. Webb's mirrors, floating 1,000,000 miles from Earth, continue to watch for evidence that the cosmos itself is running out of order. Other instruments map not stars, but geometry. The Euclid mission, launched by the European Space Agency, and NASA's forthcoming Nancy Grace Roman telescope, seek to chart the expansion of the universe with exquisite precision by measuring how galaxies cluster, how light bends through gravitational lensing. They probe the mysterious force called dark energy, the driver of cosmic acceleration. If expansion accelerates unevenly, if signals arrive in ways geometry cannot explain, it may hint at ruptures in space-time itself. Roman will measure the distances to millions of galaxies, checking whether cosmic messengers keep time with Einstein's equations. If not, it could mean the very fabric of causality is unstable. Beyond telescopes and detectors lies a quieter revolution. Quantum networks stretch entanglement across continents, linking photons in Vienna with partners in Beijing with no delay. No signal traveling in between. Each experiment tests whether entanglement can be used to transmit information, to defy relativity's chains. So far, no message has been sent faster than light. Yet the correlations persist inexplicable as quantum networks grow. Entanglement becomes a global experiment in causality. If one day information does slip through, it would mean that the signal arriving too soon is not anomaly, but principle, the birth of a new physics. In Geneva, the Large Hadron Collider smashes protons together at nearly the speed of light, probing the Higgs field, the energy landscape that defines the stability of matter. The Higgs boson's measured mass suggests an unsettling possibility. Our vacuum may not be truly stable. Instead, it could be metastable, poised to collapse into a lower state. If triggered, a bubble of new physics would spread at light speed or faster. To some theorists, an early signal could be the tremor of vacuum instability, a whisper of collapse waiting to come. Colliders continue to refine the Higgs measurement, chasing hints of whether our universe is permanent or temporary. Scattered across the Milky Way are pulsars, rotating neutron stars that sweep beams of radio light across Earth with perfect regularity. They are the universe's clocks, ticking with stability unmatched by any machine. By timing dozens of pulsars together, scientists build pulsar timing arrays capable of detecting gravitational waves, not in milliseconds but over years. Recently, They revealed a background hum of low-frequency waves ripples from ancient black hole mergers. But pulsars can do more. If signals arrive earlier or later than predicted, they may reveal not only gravitational waves but anomalies in causality itself. The galaxy becomes a laboratory for time. The Laser Interferometer Space Antenna leases a planned mission that will place 3 spacecraft millions of kilometers apart, forming a triangle in space. By bouncing lasers between them, LISA will listen for gravitational waves too vast for Earth's detector's waves from supermassive black holes. From the earliest moments of the universe, if any mission could catch a signal arriving before its cause, it is LISA, a ripple from cosmic dawn, reaching us before light, before matter, before stars. It promises to test the very order of time itself. Beyond physical instruments, supercomputers run simulations of universes, pushing equations beyond current time. They model how galaxies dissolve, how black holes merge, how expansion accelerates. Some predict stability. Others predict collapse, rip, or decay in these simulations. Signals sometimes outrun expectations, slipping across boundaries. Though artificial, they mirror what telescopes and detectors hint, that the universe may not keep time with its own laws. Never before has humanity possessed such a chorus of tools. Detectors buried in ice, telescopes floating in the dark, colliders smashing particles, computers simulating eternity, networks entangling photons across continents. Each is tuned to ask the same question: is the signal that arrives too soon real? Or is it illusion? If real, then space-time is not the unbroken stage we thought it to be. It is fragile, porous, inconsistent. If illusion, then the mystery remains. Why does nature so often hint at rupture? The pursuit continues, not because answers are near, but because questions are unavoidable. The universe offers signals, and humanity builds tools to catch them. Whether they arrive late, on time, or too soon, each one reminds us that physics is not complete, and in the silence between detections, one question waits. Will the next signal prove that reality is stable, or that time itself is broken? The story of the signal that arrived too soon is not only a tale of physics, it is a meditation on fragility and the possibility that even the laws of reality might waver. Humanity has long sought certainty in the universe, stars as fixed guides, time as the steady flow, causality as the unbroken chain. But what happens when these anchors loosen? When the signal we measure whispers that the cosmos is not as consistent as we thought? Time, to human beings, feels absolute. Clocks tick, days pass, the sun rises and sets, cause leads to effect. This rhythm gives life order, meaning, and continuity. Yet every anomaly, every neutrino that arrives before its light, every entangled particle that defies distance, every gravitational wave that ripples ahead of the storm reminds us that time may not be as linear as perception suggests. If signals can outpace causality, then perhaps the future already exists, waiting beyond the horizon, sending tremors into the present. Perhaps past and present are not distinct, but woven into a tapestry that folds back upon itself. This fragility of time does not only challenge science, it unsettles philosophy. For if time bends, what of memory? What of destiny? What of choice itself? Humanity's small place, standing on a small planet around an ordinary star, humanity presumes to measure the tempo of the cosmos. With detectors buried in ice, mirrors suspended in vacuum, and satellites sailing 1,000,000 miles from Earth. Fragile beings attempt to catch whispers from across eternity. The signal that arrives too soon humbles us. It reminds us that the universe is not written for our understanding. The laws we cherish may be temporary scaffolding, useful but incomplete. Yet there is also dignity in the attempt. To ask whether causality is absolute is to acknowledge that knowledge itself has boundaries, that those boundaries can be pushed. If the signal that arrives too soon is real, it is terrifying. It implies that effects might precede causes, that futures might bleed into pasts, that reality might collapse into paradox. A universe where signals outrun time is a universe where certainty dissolves, and yet it is also wondrous. It suggests that existence is richer than our equations, that beyond the surface of physics lie deeper rules not yet glimpsed. To fear instability is natural. To wonder at mystery is essential. Every great scientific revolution has carried this dual weight. When Copernicus displaced Earth from the center, when Darwin unsettled the origin of life, when Einstein bent time and space, each discovery destroyed certainties, but revealed beauty. The signal too soon may follow this path, an omen of collapse, or a dawn of deeper understanding. There is another reason the story resonates. It mirrors mortality. Just as a signal may arrive before its cause, so too does death remind us that life's sequence is fragile. The universe itself may not be eternal. Space-time may rupture, decay, or vanish. In contemplating the instability of reality, humanity confronts its own impermanence. Yet this confrontation is not despair, it is illumination. For to know that time may fail is to recognize the value of each moment, fragile and unrepeatable. The tools of physics, telescopes, detectors, colliders, will continue to test the anomaly. They may prove that every early signal has a mundane cause: dust, delaying photons, instruments miscalibrated, models incomplete. But even if explained, the mystery lingers. For the possibility has been opened. Reality might not always obey itself. In this, the cosmos becomes not a perfect machine, but a manuscript. Its pages, sometimes misbound, read out of order. A signal too soon is like a poem written in the margins, an unexpected word that reshapes the story. Poets, philosophers, and scientists alike glimpse meaning in these fractures. Perhaps the early signal is not a mistake, but an invitation to imagine reality more deeply, to look beyond the visible page. Humanity lives in a universe where most of existence is invisible, dark matter unseen, dark energy unexplained, quantum fields uncertain. To receive a signal too soon is to be reminded that mystery is not the exception, but the rule. If the laws of physics tremble, it does not diminish knowledge, it expands it. Every limit revealed is a doorway to a greater landscape. The signal that challenges causality beckons us to step through, to accept that reality is stranger than the comfort of clocks. There is hope even in instability. If space-time can bend, rupture, or send messages ahead of time, then perhaps it can also heal, transform, and reveal deeper truths. Some physicists dream of hidden dimensions, of universes alongside ours, of wormholes linking distant stars. Others imagine space-time as emergent, a pattern arising from deeper quantum substrates. In both visions, tearing or bending space-time may not end reality, but reveal its foundation. Thus the signal that arrives too soon may not be prophecy of collapse, but promise of discovery. In the end, the story is not about a single detection, a single anomaly, It is about the courage to ask whether the universe is consistent, whether time is stable, whether reality itself can fracture. The cosmos may remain coherent, the signals may one day be explained, or they may reveal truths so profound that relativity and quantum theory become but chapters in a larger book. Either way, the search is not wasted, for in chasing the signal that outruns time, humanity learns humility. It learns to listen carefully, to doubt certainty, to embrace mystery. And it learns that science is not only measurement, but reflection, that physics is also philosophy, written in the language of stars. Imagine again the cosmos as a vast ocean of silence. Light drifts slowly, carrying the memory of stars long dead. Gravity ripples through the void. Neutrinos stream, nearly invisible. Entangled particles whisper across infinity. And then something arrives too soon. A signal, subtle and haunting. A reminder that the universe is not finished, not closed, not fully known. Whether error or truth, omen or promise, it calls us to wonder, to recognize that causality itself is not guaranteed. That reality may not be fortress, but fragile tapestry, and perhaps, in the unraveling of space-time, humanity will glimpse not an end, but a beginning, not collapse, but revelation. For the signal that arrived too soon is less about the universe betraying its rules, and more about existence reminding us that there are rules still unwritten. The cosmos is not a clock, but a mystery, and time, perhaps, is not a river, but a veil.